Humans have always made tools, but at some point those tools became weapons. In the earliest days, a rock tied to a stick could give someone an edge in a hunt or defend against a predator. That simple innovation, essentially extending human reach and force, was the birth of weaponized technology. But what began in prehistory with sticks and stones eventually accumulated in machines of war, so advanced that they could strike targets across continents in seconds. This isn't just a story of tools getting sharper or stronger, it's the story of how power and conflict drove invention, and how each leap in weapon technology reshaped societies, battles, and ultimately, the world. Let's start at the beginning, or at least as early as we can trace it. Long before metalworking, humans were using rocks and sharpened sticks defensively and offensively. These weren't refined weapons, but they established a pattern that never really changed. Humans using objects to extend force beyond what the body alone could do. As agriculture took hold and settlements grew, conflict became more organized, and once conflict becomes organized, tools become specialized. Around 3000 to 2000 BCE, humans began working with copper and bronze. Civilizations in places like Egypt started forging weapons instead of simply shaping them. That difference matters. Forging meant control over shape, strength, and durability. Bronze swords and spearheads didn't just hit harder than stone, they lasted longer and could be reproduced more consistently. That gave rise to something new: professional armies. By around 1200 BCE, iron began replacing bronze. Iron was harder, more abundant, and ultimately more scalable. Empires like Assyria and later Rome didn't just succeed because of strategy, they succeeded because they could equip large numbers of soldiers with reliable iron weapons. Warfare was no longer just about individual strength or skill, it became about production, logistics, and access to resources. But for all their advancements, these weapons still depended entirely on human strength. Every strike, every throw, every impact came from muscle. That limitation remained in place for thousands of years, until chemistry changed everything. Gunpowder, first discovered in China around the 9th century, wasn't meant to be a weapon at all. It was the result of experimentation by alchemists searching for immortality. What they created instead was a mixture of potassium nitrate, charcoal, and sulfur, a compound that burned rapidly and produced expanding gas. At first, it was used for fireworks, but it didn't take long to realize that controlled explosions could be weaponized. By the 10th to 12th centuries, early gunpowder weapons like the fire lance began to appear. It was crude, essentially a spear with a tube that shot flames and fragments, but it introduced a completely new idea: using chemical energy instead of human strength to deliver force. That idea evolved into the hand cannon in the 13th century, a simple metal tube closed at one end, loaded with powder and a projectile. When ignited, the expanded gas forced the projectile out at high speed. That basic principle controlled explosive force inside a chamber. It's still how modern firearms work today. As these weapons spread into Europe, they began to evolve rapidly. By the 15th century, the matchlock mechanism was introduced, allowing a burning cord to ignite the powder with a trigger. It sounds simple, but it was a huge leap, turning firearms from clumsy tools into usable weapons in real combat situations. From there came the arquebus, and then the musket in the early 1500s. These weren't invented by one person, but developed collectively by gunsmiths, pushing the limits of metallurgy and design. Muskets were powerful enough to penetrate armor, and almost overnight, centuries of battlefield tradition began to collapse. Knights in steel armor, once nearly untouchable, were suddenly vulnerable. Power shifted from heavily armored elites to organized infantry. And this is where something deeper starts to happen. Weapons aren't just improving, they're forcing. And this is where something deeper starts to happen. Weapons aren't just improving, they're forcing society itself to adapt. Then after all that, came the pistol, a smaller, more personal version of these early firearms, first appearing in the mid-1500s. Pistols were rough and unreliable at first, but they introduced something entirely new: portability. Now, power could be carried, concealed, and used at close range by a single individual. Over time, gunsmiths refined these designs, improving balance, ignition systems, and the durability. By the time Samuel Colt patented his revolving cylinder in 1836, firearms took another leap forward. His design allowed multiple shots without reloading, something that dramatically increased both efficiency and the lethalness. But just as important as the design itself was how it was made, Colt pushed forward the idea of interchangeable parts and mass production, meaning weapons could now be manufactured at a scale with consistent quality. At the same time, firearms themselves were becoming more advanced internally. Flintlocks replaced matchlocks, then percussion caps replaced flintlocks. Each step made weapons more reliable, faster, and less dependent on environmental conditions like wind or rain. And then, rifling changed everything again. By cutting spiral grooves into the inside of barrels, bullets could spin as they traveled, dramatically improving accuracy and range. That small mechanical detail reshaped entire battle strategies. By the time we reach the modern era, weapons are no longer just tools or even machines. They're engineered systems built from layers of science. Take a modern pistol, for example. It may look simple, but every part of it is intentional. The frame is often made from high-strength polymer, a material engineered from petroleum-based chemicals, designed to be lightweight but incredibly durable. It resists heat, absorbs recoil, and doesn't corrode like metal. The barrel and slide are made from steel alloys, iron combined with elements like carbon and chromium. These metals are heat treated, meaning they're exposed to high temperatures and cooled in precise ways to strengthen their internal structure. That's what allows them to withstand repeated explosions inside the chamber without deforming. Even the ammunition reflects centuries of advancement. The casing, usually brass, expands under pressure to seal the chamber, then contracts for ejection. The propellant inside, smokeless powder, burns in a controlled way, generating expanding gas rather than an uncontrolled blast. And the primer, often made with sensitive compounds like lead stiffener, is designed to ignite instantly when struck. Now scale that up to the rifles like the AR platform. These rifles, originally developed by Armalite, are built for modularity and precision. The receivers are often made from 7075 T6 aluminum, a material also used in aerospace because of its strength to weight ratio. The barrels are machined with extreme precision and are often treated with chrome lining or nitriding to resist wear. Inside, the rifling stabilizes each round through spin, allowing for consistent accuracy. What really sets these rifles apart is the gas system. Instead of manually reloading, they redirect some of the gas from firing to cycle the weapon automatically. That means each shot helps prepare the next one, a level of efficiency that would have been unimaginable just a few centuries earlier. And then you move beyond firearms entirely. Grenades, for example, rely on controlled detonation. Inside a typical fragmentation grenade is a high explosive-like composition, which includes RDX and TNT. These aren't just powerful, they are stable enough to be handled safely until triggered. Once detonated, they produce a supersonic shockwave that shatters the outer casing into high-speed fragments. Flashbangs take a different approach. Instead of destruction, they focus on sensory overload. Using compounds like magnesium and oxidizers, they produce an intense flash and deafening sound, temporarily overwhelming vision and hearing without relying on a lethal force. And then the big boys, missiles, where weapons fully merge with advanced engineering. Modern missiles are built from materials like titanium, aluminum alloys, and carbon composites, designed to survive extreme stress and temperature. Their propulsion system often rely on solid rocket fuel. Mixtures containing oxidizers, like ammonium perchlorate, and fuels like powdered aluminum. When ignited, these compounds produce massive thrusts propelling the missile forward. Guidance systems layer on even more complexity, using GPS, radar, or infrared tracking to adjust course in real time. At that point, you're not just looking at a weapon anymore. You're looking at a fusion of chemistry, physics, computing, and engineering. And when you step back and look at the entire timeline, from the first sharpened stone to modern guided systems, a pattern becomes clear. Every step forward in weapon technology wasn't just about making something more powerful. It was about understanding the world at a deeper level, understanding materials, energy, motion, and control. Steel had to be mastered, chemical reactions had to be controlled, physics had to be applied with precision for it to all work together. From a rock tied to a stick, to a musket forged by early gunsmith, to a modern rifle or even a guided missile, every advancement is built on knowledge layered over time. The tools changed, the materials changed, even the scale of it changed. But the driving force behind it all, the need for survival, control, and advantage, that's the one thing that never really did. Human nature.